In this tutorial, I will solve the shallow truss problem with the static Riks step and apply load control strategy to solve the problem. The tutorial is done with the 3D Experience release 2022x. Okay, let me just say a few words about this problem. Uh, we, we're dealing with a two-dimensional truss. This is called a shallow truss because, first of all, if you take a symmetry to do half of this problem, what you have is the configuration below, and this offset is Z, and the length of the link is L. If Z is much smaller than L, it is referred to as the shallow truss. This problem was done in earlier videos, using several strategies. I started first with the uh, static step, not static Riks step. So I did it there, uh, but when you solve it as it is with half the model under load control, it actually does not converge. Okay, so basically crashes after a while. But if you solve the displacement control, and in the next video I've done that, it does converge. So what you want to do today is to solve the same problem without a spring, however, as a static Riks step and load control. And the reason, of course, is that sometimes displacement control is not feasible, and therefore you have no choice but to apply the load, specify the load, and that being the case, you can't do it as a static step, you have to do it as a static Riks step. Now, the reason that it does not converge in the situations that I described is that the load deflection curve actually has a snap-through behavior. So this is a limit point, there's a limit point here. Between these two limit points, the structure is unstable. So it's because of this that the load application does not converge. Okay? Now, these videos are prepared for people who want to do certain classical problem with the native solver of the 3D Experience 2022x, which actually is the old Abacus program, implicit program. However, the interface looks different, some of the functionalities are different, and therefore is essentially a brand new package that you're discussing. Uh, so this is why I'm preparing these videos. Okay. Now, again, no stabilizing spring. In other words, in the first one that I did, because I wanted to apply load control and static step, I had to put a stabilizing spring here, and it worked. However, we're not modeling the spring. This is a summary of what I just said. If you use the static step and load control, the code will abort. If you use static Riks step, that's what I'm going to do right now, under load control, it will run. Okay? However, first of all, static Riks step is also known as the arc length algorithm or arc length method, but there are some restrictions associated with it. And the most severe one, and it actually basically the only one, is the load proportionality. Okay, in other words, all loads rise and fall with the same scalar factor, and that may not be the case in the particular problem. Now here are the icons. This is the static step, the regular one that we have used before, and this is the static Riks step. You can see like that. This is a description for a static step, something that you probably know. But the static Riks step says configuration configures a Riks analysis procedure to predict unstable geometrically nonlinear collapse of structures. So that's the category of problem that we're in the category of problem that we're dealing with. Now there is some good references here, both the textbook and this video segment. There is an analytical solution to this problem, which we're going to be using for comparative purposes. It's right here. And the data that I'm going to take from those two references is actually over there. And I will apply a load of 13.2 Newton. This formula gives you force versus displacement. So I will apply a load of 13.2, okay? And I expect to get a displacement of 55, okay, downward. The So when you look at it, this is actual plotted with the same parameters. So 13.2 is roughly here. See that? Roughly here. See that 13.2 is roughly here. So when I apply this thing with Riks step or a static step, what I should go, there is 13.2 roughly there. You should go down to 55 millimeter. Okay. Here's the documentation from the 3D experience for this algorithm. And notice that the only restriction is the method is appropriate for cases where the loading is proportional. Okay, we can do very complicated problems, and there is some more down here, and I'll leave it to you to look at it. Okay, now we're going to model the problem in 3D experience. Okay, so I have started a part file in the part design application, and I'm going to create my geometry. So let's do 2 points here, 0, 0, 0, and another one with y of 249, 2499 and 875, and an offset, Z offset of 25 millimeter. Okay, so this creates actually the 2 points that I need, and I'm going to make a line in between them. So back to standard, a line between this point and that point, and I'm going to hide these 2 points so that I don't inadvertently put any restraints or loads on them. So hide this and hide that. Okay, let me rename this thing. So under properties, I'm going to call it static Riks, static Riks. Okay, and I'm going to save this. All right, let's go ahead and get our material, create our material. Okay, so we go to tools, create a material. Let me call this thing static Riks. Yep, February 28th. And make sure that the simulation is checked. It is. Okay. This is going to be created, but it's a blank template. Basically, I have to add my information in it. So that will be static Riks. That was not the one. So let's go ahead. Let me refresh this. Right there. Right click. Right click. Simulation. Structural. Abacus multiphysics. Mechanical. Elasticity. And the value that I have is 500,000. 3, 4. Newton per millimeter squared. Okay, the Poisson ratio 0 because we are using link elements. That's irrelevant. Okay, now I do right click, apply, and close this. I don't need it. Apply to this this part that I created, and green check mark and save. That takes care of our model. So now we're going to go to structure model creation. We're going to ask for a blank empty FEM template. Okay, and then meshing a beam element. Select this line, and notice that for the mesh size I put down 2500 millimeter, and that means that there's going to be one line through the length of this line. The length of this is 2500 millimeter. Good. Under the properties, under one-dimensional properties, this is 3D, 2D, 1D. We're going to use a link element. So all we have to do, notice notice the material is properly checked. All we have to do is the cross-sectional area on 100 millimeter squared. Okay, that takes care of our finite element model. We're now going to go, let me also save this. We're now going to go to structural scenario creation. Okay, so look on the finite element model. I'm going to choose the one that I created. Because you may have several different finite element model, discretization, etc., and you can pick and choose, but here there's only one. Now, under the procedures tab where we are right now, this one is a static step. I don't want it. This is the static Riks step. You click on it. Now, notice that you have two choices. You can do automatic arc length incrementation. Okay, or and then you have to start you have to give it some default, either use the default values or initial arc length and total arc, etc., or you can do a fixed the fixed arc length value and just use for now I'm going to use this one is fine, but uh, let me actually make this thing smaller. Okay, let me make this thing smaller. Point one. I want to remind you that the fixed strategy is not necessarily a good one, but and for realistic problem, for complicated problem, uh, things that are coming from real world, you may want to use the automatic one and then fool around with these parameters that you have to specify. Some may work, some may not, etc. So it's more than just saying go ahead and do it once with a fixed step. Okay, now I will come back and show you what the story about the stopping criteria is. Okay, I'll come back. Let me say okay. All right. So as far as the restraints go, uh, fixed displacement, this end. Now, if you're having a hard time picking it, you may want to hide this green thing, which represents the link with that diameter that is specified. Now you can probably have a better luck of choosing it right there. Okay, and X, Y, Z are free. That's a pin, and at this end it can go up and down. Sorry, it can go up and down, yeah, but nothing in the direction X or direction Y. Now, as far as the load goes, I'm going to apply this is going to be a load controls boundary condition, and that means I will apply the load. And remember, if this is the general static one or static step, this will not converge. Okay, we already saw that in the first video. Unless I put a spring there, a stabilizing spring, or I make it a displacement control. But I want to show you that with Riks method, you can actually make it work. So minus 13.2 is the load that I'm going to apply in newtons, and that should result in a displacement of 55 millimeter. Okay, say okay. All right. Now, before I simulate, since I need the point displacement, the force displacement curve at this node, I'm going to have to ask for some data to be basically retrieved or extracted. So displacement, I want translation. Okay, the entire model, although there's only two nodes here, one of them is fixed, the other one is just the point that I want. So be careful when you use entire model for the problem with a lot of nodes and things of that type. And then we also want a concentrated forces, because I want to plot the force displacement curve, the force being this concentrated force, and the displacement, of course, is horizontal displacement. Good. Okay, so let's save this. Very good. So let's do a model check. Model check. So that if there are any gross mistakes, something that I forgot, etc., is going to pop up this stage. Okay, green check mark, no issues. And then we're going to do simulation check. Certain other things can become apparent in this stage. There are warning mistakes, etc. Okay, I'm just going to be fairly fast. There may be warning. There is a warning. You can see that, but as long as I don't get error, it's a bad practice. But I don't check my warnings unless things go crazy. Okay. All right, that's done. Now we're gonna run it. I just caution you that I'm doing fixed step, making my job easier. Uh, that may not be possible, feasible, a good idea in more complicated situation. I don't like this message that I got here. Arguments are inconsistent. Modify the arguments. I don't like that, but anyway, let's see what happens here. Yeah, so let's see if it's doing any iterations here. Yeah, so far so good. It's down to 300th iteration. Actually, I would rather call it increment, not iteration. Increment. Unfortunately, some of these messages, like the one that I got, are not very uh, explanatory. So you really don't know what they're saying, and in some cases you can't even uh, get down to the meaning of that particular message. We'll see. This one hopefully it'll work. I'm not going to worry about that. Yeah, I didn't get any error messages. Yeah. Excuse me. It's extracting the results here. So I will get a displacement value, but it's going to be well above 55 millimeter that I was looking for. Because remember, I applied a load of 13.2 downward, and that theoretical solution told me that the displacement is going to be 55 millimeter. But you will see here that probably the displacement is well above the 55 millimeter. That's because it keeps increasing the load, and at some point when it reaches increment 1000, it stops. So if you look at the displacement and the final step, final increment, not the final step, just bear with me for a second. If you go all the way down, you see 130 millimeter. But what I wanted this thing to have a stop where the displacement was about the 55 millimeter. Okay, so that's probably way at the beginning, somewhere goes to the beginning of this. 54, oh yeah, okay, 50, okay, 55. So this increment corresponds to the load of 13.2, but this thing gave me well after that, values after that, okay? So let me do the following. We're going to come back and fix that. The other thing I want to show you is that when I try to get the force displacement curve, it by no means resembles this. And we're going to find out why, justify it why. So let me go to these results, by the way. These plots, I'm going to deactivate the displacement. I'm going to deactivate this. Okay, good, good. Okay, so let's try to plot the force displacement curve. Here is the XY plot from field. So I want to select this, first of all, this point. Okay, and I want to plot the displacement, so that's UT translation at that point. Now we can do the magnitude, or we can, yeah, magnitude is fine. So this curve. Notice that this is displacement, not versus time, it's versus arc length. Fine. Let's do another one. Change this thing to that CF that I asked for. Same node over there. And I'm not going to use the magnitude, because if you get the magnitude, what happens, the plot that you get is going to be flip these things so that everything's positive. So just be careful here. I'm going to use component 3. If you forget to leave it magnitude, you don't get exactly what you expect, but something close to it. And you say apply. So notice that this is force versus arc length. So what I want to do now is to plot this force versus the displacement in the previous plot. So close this, okay? Notice that two plots have been generated here, okay? So we go here to, yeah, I don't need these. So I go to the XY plot from expression, okay? So go to f of x, right there, see, f of x. You do combine. The first one is a translation. The second one is the force, and say apply. You see, first of all, I want to flip this thing up, okay? Because remember, when you look at this plot as a function of displacement, it's plotted so that, it goes up, it doesn't come down. But that's easy to do, so we're going to do a little bit of a, let me close this, okay? I'm going to take this last one, the last one, and I'm going to multiply it by -1. There, so it went up. But the thing is that this graph by no means looks like this. That's because I let it go to a much higher loads. When this thing becomes higher, 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 then actually it dwarfs all that variation down here. So it looks as if this is just growing up. However, if you look at it carefully, it goes up and it comes down. So I don't want it to go above, below, or I don't want it to go more than 57 millimeter. Okay, so let me cancel that, close all of these, and we go back to our back to our Riks step, which was here. This is the Riks step. Remember, I made it fixed incrementation stopping criteria, and I'm going to say, hey, don't go for translation, don't go in the direction 3 vertical direction more than 50 57 millimeters. Okay, say okay. Oh, it I forgot to pick the point. So you put a restriction on the point stopping. Okay, these are still there, but I have to select the point. See, this node, this node. I said, do not let this node Go more than 57 millimeter. Okay, good. So let's save this and run it. Unfortunately, you have to run it because basically you change your Riks step. So that's fine. I'm not going to check these things. I'm just going to run it. All the hard work that we needed is already done. So when I plot, go to the last increment, it's not going to be 130 that I had before. It's going to be 57 because I said stop at 57. And then we're going to update our force deflection curve, and it should look just like that. I didn't get to the bottom of this. I'm not quite sure what this thing does. This message. Yeah. If you had, I think in my fixed step, I changed it to point 0.1. If you change it to something bigger, you may get a jagged curve, but that's something you can try it. I think I changed my increment in the fixed step from 1 to point 0.1, if I'm not mistaken. Yeah, or 0.01, something like that. The bigger you make that thing, the faster it's going to run, but at the same time, the I don't know, the less detailed information on the curve you're going to get. That's why instead of being a nice smooth curve here like that, you may have something jagged, which throws you off. It should be done fast. So let's see now, where is iteration? Where are we now? Maximum is 1,000. It may stop before 1,000, I'm not sure. Oh, looks like it's going 1,000. Okay, extracting results. I think has reached the end. Yep. Should be there. Okay, so let's close that. Okay, so on the displacement, I want displacement. I change it to displacement. And right now it's over here. It's not the last increment. All right, just if you go to the last increment, see that? That should be 57. Uh, Actually, I may have to, that's okay, because something that I did, unfortunately didn't work. So let's go ahead and see what happened here. Uh, let me go ahead and check my Riks step for stopping. Where's that Riks step? I tried to make it stop at okay. You know what? What I'm gonna do? This is direction 3. What I'm gonna do is I'm gonna make this thing. How about making it minus? Let me see. Let me try minus. See whether it. Okay. Unfortunately, we have to run it again. Another couple of minutes. It stopped a lot earlier. You can see that. Okay, very good. So let me close this. If you look at it carefully, it's didn't go all the way 1,000. This is the last one. See, it didn't go past 57. And what we want is around maybe 55 or something. This corresponds to a load level of 13, roughly 13.2 Newton. But let's plot our curve right here. Right here, this expression, remember that? Apply. There we are. See? Looks just like that. Numbers are the same. The 13.2 that we applied, 13.2 Newton that I applied is somewhere here. And when you trace it, you're going to get roughly 55. Now, one other thing I'm going to do before I quit, and that is to go to the Riks step. Where is this? Right here. Let me close these. Okay. Remember I made this thing 0.1? I told you that let's take it as 1 and run it. The stopping criteria is still the same. You can see that. Let's see what happens to the outcome. This is going to be very fast, but very wrong. Let's give it a try. If it finishes, if it finishes, then it's going to get a jagged curve. But I'm not even sure if it will finish. But it's worth trying. See, iteration. This may be so big that basically it cannot reach a solution, but I'm not sure. Oh, okay. See, finished it. Okay, there we are. And as far as the numbers go, see that? As far as the number goes, the last step, 57, didn't go past that. But if you look at this plot, I'm sure it's going to be very jagged. There we are. Okay. All right. Good luck. And try on your own, do the automatic time stepping, please.